What if the universe itself is not still, but restless, stretching, pulling,
Oh.
fleeing from every point into a vastness without end? It was in the 1920s, upon the heights of Mount Wilson in California, that this question first took shape in the trembling light of distant galaxies. Through the 100-inch Hooker telescope, the largest of its time, Edwin Hubble peered into the depths of the night and traced the faint glow of nebulae that until then were thought to lie within the Milky Way. The light carried with it a hidden signature, a shift toward the red, a stretching of wavelengths that whispered of motion. These galaxies were not standing still. They were retreating, each one sliding away into the darkness, as though driven by an unseen wind. It was a revelation that shattered an ancient belief. For centuries, the cosmos had been imagined as eternal and unmoving, a static dome where stars circled forever in quiet order. Even Einstein himself, reluctant to abandon the comfort of stability, had introduced a mathematical fix, the cosmological constant, to hold the universe steady against collapse. But Hubble's findings dismantled that illusion. Space itself was swelling, carrying galaxies apart like driftwood on a boundless sea. This was not a minor correction. It was a cosmic upheaval, the realization that the universe had a past, a birth, and perhaps even a destiny. The discovery of expansion transformed cosmology into a story not of permanence, but of change, of beginnings and potential endings written into the very fabric of space-time. What Hubble uncovered was not just the motion of galaxies, but the first glimpse of a universe alive, expanding, and filled with mysteries that would redefine humanity's place within it. The discovery of expansion was not a quiet addition to science. It was a rupture, fracture in humanity's oldest comfort that the heavens were eternal, that the cosmos stretched without beginning and without end. For thousands of years, the universe had been painted as a stage of permanence. The stars might move in slow procession, galaxies might swirl in eternal spirals. But the stage itself, the canvas on which all was drawn, was thought to be unchanging. Hubble's revelation struck at that ancient foundation. If the galaxies were racing away, then long ago they must have been closer. And further back still, closer than imagination dared to conceive. The equations of relativity did not resist this implication, they demanded it. They pointed toward an origin, a single moment when all space, all time, all matter and energy were gathered into one indescribable point. It was a shocking birth, the Big Bang, not an explosion in space, but the explosion of space itself. Not fire spreading through the universe, but fire creating the universe. A singularity where the known laws of physics collapsed, where densities became infinite, and where mathematics itself faltered. The very suggestion was unsettling. Scientists of the early 20th century were divided. To some, the idea of a universe with a beginning was too close to metaphysics, too tangled with theology. To others, it was the inevitable truth, written into the redshift of galaxies and the relentless logic of Einstein's equations. A cosmic genesis was no longer the language of myth. It had become the language of physics. Yet if there was a beginning, the thought that followed was equally haunting. Could there also be an end? If expansion was the destiny of matter, might contraction someday be its fate? Would gravity reclaim what expansion had unleashed? The mathematics of singularities, developed decades later by Roger Penrose and Stephen Hawking, deepened this fear. They showed that under general relativity, singularities are not optional curiosities, but unavoidable consequences. If the universe could begin with one, it could end with one. Their work suggested that singularities were not defects in the theory, but pillars of its architecture, gateways where the ordinary rules of space and time collapse into silence. The scientific shock was not only in the scale of the claim, but in the philosophical weight it carried. A beginning meant finitude. It meant history. It meant the universe was not an eternal machine, but a story unfolding in time. And stories, by their nature, suggest endings. The expansion was no longer merely about galaxies drifting apart. It was space-time itself, elastic, dynamic, alive. The fabric of reality could stretch, it could curve, it could rip. And in this pliability lay the terrifying possibility that the universe's destiny was written in the same equations that described its birth. Some clung to the hope of a steady state. Somehow, as galaxies fled outward, new matter would continuously emerge to fill the gaps, keeping the cosmos balanced, unchanging, infinite. But one by one, the observations broke that hope apart. The cosmic microwave background, discovered in 1965, sang the afterglow of a hot, dense beginning. Its faint hum across the sky was an echo of the moment when light first escaped matter, a relic of the fireball that had birthed everything. No steady state could account for such a relic. Only a singular genesis could. The Big Bang was no longer speculation. It was evidence, yet evidence brought not comfort, but unease. The mind recoils at singularities because they defy imagination. What does it mean for everything to emerge from a point smaller than thought? What does it mean for time itself to have a beginning, for before to have no meaning at all? Hawking once remarked that asking what lies before the Big Bang is like asking what lies north of the North Pole. The question itself dissolves under the weight of space-time's geometry. But if the mind cannot travel before, it can wander ahead. If there was a birth, what form will death take? Will the same equations that unveiled the beginning also dictate the ending? Two fates emerged in the language of cosmology. One was contraction, a big crunch, where expansion would one day slow, halt, and reverse. Galaxies scattered for billions of years would be drawn back together, their light compressed into searing heat until all was crushed once more into singularity. A universe that breathes outward, then inward, perhaps to begin again. The other fate was eternal expansion, a big freeze. Galaxies retreating beyond sight, stars burning out, matter decaying, until only darkness and the thin whisper of radiation remain. Cosmos still expanding, but expanding into silence. Both possibilities were born from the same revelation, that the universe has a story, a timeline, and therefore a destiny. The shock of expansion was not only that it began, but that it may end. For the first time, humanity confronted not only its own mortality, but the mortality of the universe itself. The discovery of expansion had reached beyond astronomy. It had reached into philosophy, theology, even existential dread. The cosmos was no longer the eternal backdrop for human history. It was itself a fragile character in the drama of existence. With a birth, with an unfolding, with a fate still hidden, and perhaps the greatest fear lingered in silence. If space-time itself can begin and end, then what does it mean for the reality in which we live? What lies outside the story? What lies beyond the beginning and beyond the end? This was the revolution of the 20th century. Expansion had revealed more than motion. It had revealed fragility, impermanence, and the profound mystery of existence itself. The shock of cosmic expansion did not end with Hubble. His discovery was a beginning, not a conclusion. Once the truth of expansion settled into the fabric of physics, an even more pressing question followed. How fast is the universe expanding? And will that rate remain the same, slow to a halt, or accelerate into an unimaginable future? Throughout the mid-20th century, astronomers turned their instruments toward the sky to measure the heartbeat of expansion. They searched for a number, a constant that could capture the restless drift of galaxies. Hubble himself had estimated it, but his calculations placed the universe at only a few billion years old, alarmingly younger than the Earth itself. Something was wrong. Measurements were plagued by uncertainties, distortions of light, and the delicate assumptions required. When translating the shimmer of galaxies into precise distances, to refine this number, scientists needed a deeper cosmic yardstick. And in 1965, two engineers at Bell Labs stumbled into the most profound clue yet. Arno Penzias and Robert Wilson, working with a sensitive radio antenna, heard a faint noise static that would not fade. They tried everything to erase it, even cleaning pigeon droppings from the telescope's horn, but the hum persisted.
What they had found was not interference.
It was the universe itself, whispering across the sky. The signal was the cosmic microwave background, the cooled afterglow of the Big Bang. Radiation released when the newborn universe, once opaque with plasma, thinned enough for light to travel freely. This relic light, stretched by billions of years of expansion into microwave wavelengths, filled the heavens in every direction. It was a fossil of creation. With it came the chance to probe the universe's past with unprecedented clarity. Satellites like COBE in 1989, WMAP in 2001, and the Planck mission in 2009 mapped this faint glow with increasing precision. At first, it seemed almost uniform, a perfect bath of ancient light. But hidden within were tiny ripples, anisotropies no stronger than 1 part in 100,000. These faint temperature variations were the fingerprints of quantum fluctuations, stretched across the infant cosmos that would later grow into galaxies, clusters, and the vast cosmic web. The seeds of every star and planet, every breath of life, were written into those primordial irregularities. Cosmic microwave background was not just an echo of the beginning, it was the blueprint of everything that followed. From these maps, cosmologists measured the expansion rate with exquisite detail. They discovered a cosmos 13.8 billion years old, a universe consistent, coherent, and yet still filled with mysteries. Among those mysteries was a ghostly period in the earliest instant of time, a fraction of a second after the Big Bang, when expansion did not merely proceed, but exploded in ferocity. This was cosmic inflation, according to the theory. The universe ballooned faster than light itself, swelling from subatomic scales to astronomical immensity in less than a heartbeat. Inflation smoothed the cosmos, explaining why regions of the sky, separated by billions of light-years, share the same temperature. It stretched tiny quantum fluctuations into the seeds of galaxies. It was a moment of inconceivable violence, and yet it left behind a calm, ordered universe. The evidence for inflation emerged from the very anisotropies etched into the cosmic microwave background, the pattern of peaks and troughs in the CMBs. Spectrum matched the fingerprints predicted by inflationary models. Though details remain elusive, the theory became a cornerstone of modern cosmology, weaving together the mysteries of the earliest second with the structure of the universe today. But even as inflation explained the past, a new and more troubling enigma arose in the present. Astronomers in the 1990s set out to measure how expansion was changing over time. If gravity were the only force at play, then the combined mass of galaxies, stars, and dark matter should act as a brake, slowing expansion gradually, using distant Type Ia supernova as standard candles, brilliant explosions so luminous they could be seen across billions of light-years. Researchers hoped to measure the cosmic deceleration. What they found was the opposite. The supernova appeared dimmer than expected, as though they had been carried farther away by an expansion that was speeding up, not slowing down. The cosmos was not relaxing into stillness. It was accelerating into the unknown. The discovery, announced in 1998 by 2 rival teams, was as shocking as Hubble's revelation 70 years earlier. Expansion was not only relit, was gathering pace. An unseen force, repulsive in nature, seemed to be woven into space-time itself, driving galaxies apart with increasing urgency. This force was given a name both simple and mysterious: dark energy. Its nature remains one of the deepest puzzles in science. It may be the energy of the vacuum predicted by quantum field theory, yet staggeringly mismatched in magnitude. It may be a new field altogether, dynamic and evolving. Or it may signal a flaw in our understanding of gravity on the largest scales. What is known is that dark energy dominates the universe. Roughly 70% of the cosmic budget is this unknown force. It's invisible and untouchable, but dictating the fate of everything. Matter, stars, and galaxies make up less than 5%. The rest is dark matter, unseen but gravitationally binding. The universe is not made mostly of the familiar, but of the mysterious. The deeper scientists looked, the more disquieting the picture became. Expansion was not a simple curve into the future. It was a drama ruled by forces unseen. The acceleration meant that distant galaxies would one day vanish from view, receding beyond the cosmic horizon. The further the universe stretches, the less of it will remain visible, till only the nearest cluster of galaxies, bound by gravity, will share the sky. The cosmos is erasing itself from our sight. The investigation into expansion had begun with a telescope on Mount Wilson, a man measuring the drift of galaxies. It had grown into satellites, mapping the afterglow of creation, mathematicians unraveling the birth of structure, astronomers charting explosions billions of light years away. Each discovery had not solved the mystery, but deepened it. The universe was expanding faster, further, more mysteriously than anyone had imagined. And now, at the center of it all, stood dark energy, a force, invisible, yet sovereign, dictating the pace of the cosmos. The investigation had peeled back layers of truth, but what lay at the core was something stranger than any had expected. Expansion was not merely the drift of galaxies. It was the unfolding of space-time, animated by a force that even the equations struggled to capture. The deeper humanity looked, the less familiar the universe became. The revelation that expansion was not slowing but accelerating struck with the force of a cosmic thunderclap. What had once been imagined as a gentle unfurling of space, destined to relax into stillness or reverse under the pull of gravity, was revealed to be something far stranger. The universe was not merely drifting outward. It was rushing, surging, gathering momentum as if driven by an invisible tide. The shock reverberated through science and philosophy alike. Expansion, long thought to be a fading echo of the Big Bang, had revealed itself as a process not only alive but restless, refusing to diminish. The very fabric of space-time was not simply stretching, it was accelerating into mystery. If acceleration continues, the consequences are profound. Galaxies, those beacons of light across the abyss, will one by one vanish. It's not because their stars go dark, but because expansion will carry them away faster than light itself. This does not break relativity. It is not the galaxies moving through space, but space itself expanding between them. And when space grows more quickly than light can bridge, signals are cut forever. The great cosmic conversation, once alive with the exchange of photons, will fall silent. Already the majority of galaxies lie beyond reach. Their light, stretched into faint whispers of infrared, struggles to arrive. In time, only the nearest, clustered the Milky Way and its companions in the local group, will remain visible. Beyond that, darkness. The sky, once overflowing with galaxies, will become sparse. To future astronomers, the cosmos may appear empty, its true story erased by the relentless surge of expansion. This accelerating fate paints chilling visions of the universe's future. One scenario is the heat death, a slow and inexorable extinction. As galaxies drift apart, their stars burn out. Black holes consume what remains, only to evaporate through Hawking radiation. Expansion carries everything further from everything else, till even the last particles are diluted in a sea of near nothingness. Temperature approaches absolute zero. Cosmos becomes a desert of silence, still expanding, yet devoid of structure or spark. Another vision is the Big Freeze, a variation of the same theme. The universe does not collapse, nor does it tear itself apart. Instead, it stretches endlessly, growing colder, thinner, dimmer, until eternity itself becomes indistinguishable from death. Time continues, but without change. A clock ticking in, a room long abandoned. Yet darker still is the specter of phantom energy. If dark energy grows stronger with time, rather than remaining constant, it may not only drive galaxies apart, but tear apart the very fabric of bound systems. In this scenario, the Big Rip, the universe's acceleration grows so ferocious that billions of years from now, galaxy clusters are dismantled, then galaxies themselves, then star systems, planets, and finally atoms. Even the bonds of nuclei would be undone, torn asunder by the accelerating expansion of space-time itself. A cosmos not only emptied, but violently shredded into nothing. Each possibility is more unsettling than the last, and none can be ruled out. The deeper astronomers peer into the sky, the more uncertain the end becomes. The expansion does not follow a clear script. Its pace is written into equations we do not yet fully understand, driven by forces we cannot Yet measured directly, here lies one of the most haunting features of an accelerating universe: the cosmic horizon. Just as the horizon of Earth conceals lands beyond sight, the expansion of space erects a barrier beyond which no information can reach. Unlike the familiar horizon, however, this barrier is not an illusion of perspective. It is real. Galaxies exist, but forever hidden. Their light, stretched and slowed, can never arrive. The cosmic horizon is a prison wall. It grows as acceleration continues, shrinking the accessible universe around us. We live within an island of visibility, while the greater ocean of reality slips away. For every discovery science makes, more of the cosmos is lost beyond reach. The paradox is cruel. The more we learn, the less we are able to see. This horizon robs not only of sight, but of certainty. We cannot know whether the physics that governs our local patch holds true beyond the barrier. Perhaps the density of dark energy differs elsewhere. Perhaps other fates are playing out, invisible in distant realms. The universe may be vast and varied, but to us, it will always be a fragment. Bounded by walls of expansion, the acceleration deepens the sense of estrangement. Humanity, for a fleeting epoch, lives in a cosmos filled with galaxies and light, able to look back to its beginnings and out toward its grandeur. But this epoch is temporary. In the far future, the evidence of expansion itself will fade. Microwave background will stretch beyond detectability. Galaxies will vanish. The universe will appear static once more, though it will not be. To the observers of tomorrow, the story of origin may become forever unknowable. The escalation of this mystery lies not only in science, but in its reflection on existence. If expansion accelerates without end, then meaning itself is tied to transience. Every star, every galaxy, every act of life exists against a backdrop of vanishing. The stage grows emptier with each passing age, yet within this melancholy lies, for acceleration reveals the universe not as a closed book, but as a dynamic, restless story. Its fate is uncertain, its path unsettled. It could freeze, it could rip, it could evolve into a state we cannot yet imagine. This uncertainty is itself a profound truth. Reality is not fixed. Even the cosmos is subject to mystery. The deeper we look, the more fragile certainty becomes. The equations whisper possibilities but refuse to settle. Each discovery pushes the horizon of knowledge outward, even as the cosmic horizon retreats inward. Humanity stands between these two horizons, one of knowledge, one of expansion, both advancing, both retreating, both shaping the story. Of what can be known, the acceleration of the universe is more than a scientific shock. It is a reminder of impermanence written into the fabric of everything. It is the recognition that even the stars are temporary, that even galaxies can vanish, that even the universe itself may dissolve into silence, and still it expands. The mystery of acceleration demands explanation. Observations have revealed what the universe is doing, but not why. The cosmos expands, and expands faster with time. The galaxies drift apart at ever greater speeds. The fingerprints of dark energy are carved into the data, but its nature remains hidden. To confront this enigma, physicists have turned to theory, to the invisible scaffolding of mathematics, to the quantum depths of vacuum, to speculative visions that stretch imagination to its limits. The simplest possibility is that dark energy is nothing more than the energy of empty space itself. Quantum field theory predicts that even a vacuum is not truly empty. It teems with virtual particles flickering in and out of existence, ephemeral fluctuations that, though invisible, possess energy. This vacuum energy could act as a pressure, a repulsive force pushing space-time outward, and yet, when the numbers are calculated, the mismatch is staggering. Quantum physics predicts a vacuum energy density larger than observation by more than 100 orders of magnitude. If correct, the universe should have blown itself apart instantly, never allowing galaxies or stars to form. Somehow, reality is finally balanced on the edge of contradiction. The vacuum whispers of dark energy, but it whispers far too loudly in the mathematics. Here, Einstein's old idea returns, the cosmological constant. Once introduced reluctantly as a mathematical patch to preserve a static universe, it was later abandoned when expansion was discovered. But with acceleration, it finds new life. Perhaps dark energy is truly constant, an unchanging property of space-time itself. A cosmological constant would provide a steady, eternal push, ensuring expansion continues forever.
Oh.
If true, the universe would face a future of endless acceleration, cooling into a frozen stillness where galaxies recede into oblivion. But constancy may not be the final answer. Some theories suggest that dark energy is dynamic, not fixed, a field that evolves over time. This concept is called quintessence, borrowing its name from the ancient notion of a fifth element beyond earth, air, fire, and water. Unlike a constant, quintessence can vary in strength, waxing and waning as the universe evolves. In some versions, it grows weaker, allowing expansion to slow. In others, it strengthens, threatening more violent fates. Quintessence is a cosmos animated by a living field, shifting in ways yet unseen. More unsettling still is phantom energy. If dark energy's pressure is even more negative than a cosmological constant, its repulsion grows stronger with time. Expansion accelerates not steadily but catastrophically. The future becomes a countdown to the Big Rip. First, galaxy clusters are pulled apart, then galaxies themselves. Stars are torn from their systems, planets from their stars. Ultimately, molecules, atoms, even subatomic particles are shredded as space-time itself tears. The universe ends not with silence, but with annihilation written into the expansion of space. Not all theories point toward destruction. Some envision rebirth. The idea of a cyclic universe suggests that expansion is not final, but part of an eternal rhythm. The cosmos expands, slows, contracts, and collapses in a big crunch, only to rebound in another big bang. This endless cycle of bounces would erase the need for a singular beginning or a terminal end. Instead, existence itself becomes infinite recurrence, a phoenix cosmos rising from its own ashes forever. Yet evidence remains elusive. In entropy, the increase of disorder casts doubt on whether such perfect cycles could truly persist. Others extend speculation even further, to the idea of a multiverse. In the inflationary picture of the early universe, expansion may not have ended everywhere. Pockets of space-time could continue inflating, budding off into separate regions, each with its own laws of physics, each with its own fate. Our universe would then be but one bubble in a vast cosmic foam. Some regions may collapse swiftly. Others may expand eternally. Some may harbor life. Others may be sterile. In this landscape, dark energy is not a universal constant, but a local condition, a property of our bubble among countless others. This leads to one of the most controversial ideas in cosmology, the anthropic principle. It suggests that the universe is as it is because if it were any different, we would not be here to observe it. If dark energy were stronger, galaxies could never have formed. If weaker, the cosmos might have collapsed long ago. The balance appears improbably fine-tuned, as though reality is perched on a razor's edge. Perhaps in the multiverse, countless universes exist with countless values of dark energy, and we inhabit the rare one where conditions permit stars, planets, and life. Such reasoning does not provide a satisfying physical mechanism, but it reflects the strangeness of our position. We exist within a cosmic balance that seems improbably fragile. Theories and speculations reveal possibilities, but none bring closure. Vacuum energy fails by excess. The cosmological constant feels arbitrary. Quintessence and phantom energy open futures both subtle and terrifying. Cyclic models promise renewal, but struggle with entropy. Multiverse theories stretch beyond testability. The anthropic principle replaces mechanism with perspective. The expansion of the universe resists. Final explanation. Each theory illuminates part of the mystery but casts new shadows in turn. What is clear is that dark energy, whatever its nature, defines the fate of everything. Its strength will determine whether galaxies remain bound or drift into silence, whether space-time endures or tears apart, whether universes arise once more or vanish forever. Here, science merges with philosophy. Theories are not merely equations but reflections on impermanence and possibility. They remind humanity that the universe is not fixed, not secure, not eternal. It is dynamic, fragile, and profoundly mysterious. Expansion is not only a physical process. It is a mirror in which existence itself is questioned. The universe expands, but what drives it and where it leads remains hidden in the silence between galaxies. The universe expands, and the mind longs to measure its pace. Yet, in the attempt to take its pulse, a strange discord emerges. Two methods, two answers, and a tension that refuses to fade. This tension is called the Hubble constant problem. One path measures the local universe, the nearby galaxies, the brilliant explosions of type Ia supernova, the delicate flicker of Cepheid variable stars. With these cosmic yardsticks, astronomers trace distances and compare them to velocities, yielding an expansion rate of about 74 kilometers per second per megaparsec. The other path looks deeper, to the infant cosmos itself. By reading the ripples frozen in the cosmic microwave background, satellites like WMAP and Planck reconstruct the early universe's parameters, then predict how quickly it should expand today. That answer is smaller, around 67 kilometers per second per megaparsec. Both methods are precise. Both are consistent within themselves, yet the gap between them refuses to close. This is no minor discrepancy, it is a tension that gnaws. At the foundations of cosmology, perhaps unseen physics shaped the early universe differently. Perhaps new particles or forces skewed its history. Or perhaps the local cosmos holds subtle influences that bend the numbers. Whatever the cause, the universe resists the neatness of agreement, as though reminding us that its secrets cannot be reduced to a single number without struggle. To confront this puzzle, humanity has turned its greatest instruments toward the sky. The Hubble Space Telescope, orbiting Earth since 1990, has measured Cepheid stars and supernova with precision unimaginable from the ground. Its vision has refined the local ladder of distances, sharpening the higher estimate of expansion. Now its successor, the James Webb Space Telescope, with mirrors vast and infrared eyes, sensitive to the faintest light, extends this ladder even further. Webb observes Cepheids with unprecedented clarity, disentangling the dust and noise that clouded their signals. Each observation adds weight to the higher value, deepening the mystery. Soon, the Vera Rubin Observatory, under construction in Chile, will survey the entire visible sky every few nights, creating a movie of cosmic change. Billions of galaxies will be cataloged, their shapes, positions, and motions woven into a map of how structure grows under the hand of dark energy. Its legacy survey of space and time promises to be one of the most profound windows into the expansion of the universe. Watching how the cosmic web itself responds to the invisible force that drives it apart. Above Earth, new satellites join the search. The European Space Agency's Euclid mission, launched in 2023, is tasked with charting the geometry of the universe by mapping billions of galaxies across cosmic time. By tracing how light bends through gravitational lensing and how galaxies cluster, Euclid will reveal the fingerprints of dark energy on the largest scales. Soon will come NASA's Nancy Grace's Roman Space Telescope, named for the visionary who helped birth the Hubble mission. Roman will carry a wide-field infrared instrument capable of surveying vast swaths of the sky with extraordinary resolution. Its mission is explicit: to probe the nature of dark energy, to measure the cosmic acceleration with exquisite precision, and to test whether Einstein's general relativity holds across the largest scales of existence. Each telescope, each survey, each satellite is a fragment of a grand effort to chart the unseeable, to measure the immeasurable. They stretch vision across time, gathering photons that have traveled billions of years to tell their story. Yet even as the tools grow sharper, the questions grow deeper. The horizon of certainty seems always to retreat just beyond the reach of even the most powerful eyes. Beyond telescopes, even particle colliders, play a role in this cosmic search. For dark energy may be tied to the very fabric of the vacuum, and to test its nature requires exploring the quantum depths. The Large Hadron Collider, the most powerful machine on Earth, smashes protons together at near-light speeds, probing the structure of fields that permeate space. If the vacuum is unstable, if the Higgs field that gives particles their mass rests precariously in a false minimum, then expansion itself could be a fragile illusion, one day undone in a catastrophic transition. The stability of the vacuum is not merely a theoretical curiosity. It is a question about whether space-time can endure. Other experiments, deep underground and shielded from cosmic noise, search for the faint signals of dark matter, whose interplay with dark energy may hold clues. Cosmic surveys map baryon, acoustic oscillations, the subtle ripples imprinted in galaxy distributions by primordial sound waves. Together, these efforts form a tapestry of measurement, thread reaching for the truth of expansion's engine. Yet with every step forward, the enigma deepens, the Hubble tension persists. The nature of dark energy remains undefined. Telescopes see further, but the horizon of the observable shrinks as acceleration carries galaxies away. Colliders probe deeper, but quantum fields remain mysterious. The universe reveals itself in glimpses, never in full. Still, progress is undeniable. The questions we ask today are sharper than those of a generation ago. The tools in orbit and on Earth are the most precise instruments humanity has ever built. They whisper of answers, perhaps subtle cracks in Einstein's equations, perhaps evidence of new physics waiting to be found. The path forward is uncertain, but the pursuit is relentless. There is a quiet irony in this search. It is designed to bring us closer to certainty, yet what they reveal most often are greater mysteries. The more accurately we measure, the more clearly we see the gaps in our understanding. Expansion, once thought a simple drift of galaxies, has become a labyrinth of unanswered questions. But perhaps this is the nature of science itself, that certainty is not a destination, but a horizon that shifts, recedes, and reshapes itself as we approach. The universe is not merely expanding. So too is the boundary of our knowledge, stretching outward with every discovery, carrying us further into mystery. And just as the cosmic horizon hides much of reality beyond sight, the horizon of certainty reminds us that the most profound truths may always remain just beyond reach. Humanity lives suspended between them, measuring, questioning, searching, knowing that the closer we come to answers, the more vast the unknown becomes. The universe expands, and within it, humanity drifts. Fragile passengers carried on a current with no visible shore. Galaxies slide away, time flows forward, and the cosmic horizon retreats like a tide that never turns. In this silent voyage, there is no anchor, no map, no certainty of destination. We are adrift in a sea of expansion, held only by the fragile bonds of gravity that tie our small corner of space together. And yet, it is this very expansion that made existence possible. In the first moments after the Big Bang, the stretching of space-time cooled the primordial fire, allowing atoms to form, allowing matter to clump into stars and galaxies. Without expansion, there would be no galaxies to shine, no stars to burn, no planets to orbit them, no life to emerge from their elements. Expansion is creator. It gave the cosmos its shape, gave time its rhythm, and gave every living being its chance to exist. But what creates also destroys. That same expansion now accelerates, scattering galaxies into isolation, dimming the sky one horizon at a time. In billions of years, the heavens will fade into emptiness. The relic glow of the Big Bang will stretch into wavelengths so long that even the most sensitive instruments cannot detect it. The very evidence of origin will vanish. Expansion will erase the story it once revealed. It is both cradle and grave, a force that births structure only to dissolve it again. This paradox cuts deep into the human mind. We long for permanence. We crave answers written in stone, eternal truths that will outlast us. Yet the universe refuses to settle. It offers no final ground, no fixed stage. It is restless, in motion, evolving, unstable.
Else.
Its nature is impermanence itself. Stars die, galaxies drift, space-time bends and stretches. Even the laws we write to describe it may prove incomplete, temporary approximations of a deeper order, yet unseen. Perhaps this is why the question haunts us so deeply. Will expansion end? It is not merely a scientific puzzle, but an existential reflection. To know the fate of the universe is to confront the fate of meaning itself. If expansion ends in silence, does that silence diminish the lives that unfolded within it? If expansion never ends, what does it mean to live within a story without conclusion? And perhaps the question cannot be answered not within a lifetime, not within a civilization, perhaps not even within the span of our species. The time scales are vast, the force is subtle, the uncertainties profound. The universe may keep its secret long after humanity is gone, long after Earth is dust, long after the Milky Way itself is torn from sight. The pursuit of an answer is itself a fleeting act, a gesture of curiosity made by beings who know they cannot last. But there is a quiet beauty in that gesture. To ask is itself meaningful, even if the answer never comes. To search is to participate. In the universe's unfolding, to carve a moment of awareness within the vast flow of time, humanity's questions are brief sparks, but sparks that illuminate, however briefly, the darkness around them. Perhaps then, the universe is less a riddle to be solved than a song to be experienced. Expansion is its melody, beginning in a surge, a fire swelling into harmony through the birth of galaxies, and now echoing into the unknown future. But unlike a human song, it offers no final note. It may fade, it may crescendo, it may fracture into silence, but there is no resolution written into its score. We live not at its beginning or its end, but in the mysterious swell between a single phrase and an endless composition, and so humanity drifts. Fragile passengers on a current we cannot control, voyagers in a cosmos that expands without shore. Expansion gave us our stars, our worlds, our very breath. One day it may take them away. But for now, in this fleeting epoch, the universe sings, and we are here to listen.